Today we will discuss about the material nonlinearity within our partial differential equation describing the eddy current case. Since the nonlinearity is within the magnetic relativity or permeability, it is just 1 over the corresponding material parameter, we will reduce our partial differential equation to the static case, the magnetostatic case, and that is, as you can see here. So we have the curl of the material parameter, in our case the magnetic relativity, as a function of B, the magnetic induction, curl of the magnetic vector potential is equal to a given current density, for example, in a coil. So B as an absolute value is the absolute value, as we know, of the curl of the magnetic vector potential, which we have introduced in order to get a compact partial differential equation describing our magnetic field. So let's look at the nonlinearity. As you can see here, we call it the so-called pH curve. And as you can see here, we have here the absolute value of B, here the absolute value of H, and it is a heavily nonlinearity. It goes with a very strong slope and then decreases and goes towards saturation. And that we have now to take into account. Since we have written our partial differential equation with nu, let's look at our nonlinear relativity curve, which is shown here. And what is also shown here are individual points within the curve, and these are the so-called measurement points. So we do measurements, we measure B as well as H, can compute nu, the relativity or permeability, and these are just here, the individual points are connected by lines. And also, if you look here at the different values, you see strong differences at low and very high magnetic flux densities. So for example, in iron, we have a saturation at about 2.2, 2.3, up perhaps 2.5 Tesla, were more or less no further increase concerning the magnetization is possible, and the further increase is then just by the slope of the permeability or relativity according to the value of vacuum. Now, how can we solve such a nonlinear partial differential equation within the context of the finite element method? First of all, we want to go to some details concerning our pH curve and especially the relativity. The pH curve has the advantage. It is, as we have seen, a curve which is monotone, which is not the case for the relativity or permeability curve. So in this sense, we try to express it as the pH or HP curve. We do it as the H as a function of B because we have a partial differential equation for the magnetic vector potential. So when we have solved it, we get the magnetic vector potential via the curl B. And so it makes sense to use exactly this relation as shown here, that H is equal to the relativity as a function of B times B. Okay, so now we know the relativity is just dividing H as a function of B by B, and taking the derivative now with respect to B, which we write by nu prime, is in the denominator B squared, the derivative of H times B minus H derivative of the denominator, which is B, so it just remains h as a function of b. And this is important because for a Newton method we need also the derivative of the relativity, as we will see soon. Why do we do an approximation? First of all, it is clear when you do any measurements, you will also introduce measurement errors. It will not be the case that the measured values within the HB curve are totally exact. And on the other hand, we should find somehow a smooth approximation without too large slopes in order to get better properties concerning the convergence when we solve the nonlinear problem. That is why we use smoothing splines by minimizing a special regularized least squares function. Okay, so now let's see what we actually do, and that is shown on this slide. So our functional, which we are going to minimize, is as follows. We integrate over the whole range where we have the measurements of b and take here the second derivative of h with respect to b, which means that's the curvature of our problem. And we want to minimize here this curvature to have a very smooth function. On the other hand, we also want to meet the measurements. Yeah, and how we try to meet the measurements is then defined by this parameter alpha. The larger alpha, the more this whole term will be of importance, and the more we will be able to meet the measurement points. On the other hand, we more or less neglect it, we get a very smooth function. So in order to have a smooth function, alpha should be small, and therefore we need some discrepancy principle, which I will describe on the next parts here. So this is the choice of alpha. The curve will be very smooth if alpha is small, because then this term is the most important term. On the other hand, if alpha is large, then we will be very close to the measure points. And to resolve this discrepancy, we have the so-called discrepancy principles. So we set alpha equal to the largest number of a geometrical decreasing sequence like 2 to the power of minus g. So you have start with 2 and then decrease it in this sense until the difference we have in our error measurement between the measured h values and the approximated one is in the order of the measurement error. And that makes sense. It makes no sense to be more accurate as the measurement error. So with the help of this discrepancy principle, it is a good choice to optimize here your function with this least squares regularized function. Okay, now we know how to get the evaluations of our nonlinear parameter. And in a Newton scheme, as you know, we approximate the nonlinear operator. So we have a nonlinear operator, which is our partial differential equation, but at the end it will be more useful, and that we will do. We will use it already in the weak formation. Anyway, we have any nonlinear operator as a function of our magnetic vector potential A, and this we approximate by evaluating the operator at AK, so this is the current iteration we have, plus the derivative. So this classical as we have also for a Newton, for a function with one unknown. Here it is just the following. It is the Frechet derivative at the already known ak in a search direction s, as written in such a notation, where the search direction s is the quantity we want to compute, because when we were able to compute it, then we can write down it in this sense. So we have to solve this equation here. We set the nonlinear operator, clearly we set to 0. So the error we make will be the higher order derivatives we are not including. And having solved this, we can get a new iterate a at the iteration k plus 1, which is the old one, plus the increment or this search direction. And what we actually will do, we will introduce, as you can see here, this eta, because it's a question with which amplitude we go within the search direction, especially at the starting where we are perhaps far away from the solution. We need such a method, you call it line search parameter. So you do a kind of a line search approach to get the optimal eta within each iterative step. So we see the following. The computation of this f prime, our nonlinear operator. Now for us, since we are interested to get the Newton method within our finite element formulation, we will do this approximation of the Frechet derivative with a nonlinear operator, which is already the nonlinear operator of the weak form of our partial differential equation. So let's have a look at this. So as you know, the weak form, as discussed last time, is written down here. And now this weak form, which we have here, is our nonlinear operator, which has to be equal to 0. A prime, as we know, is our test function, which means the computation of the Frechet derivative is as follows, or which we approximate in first order, is as follows. We evaluate our weak form, as shown here, at ak plus s minus the nonlinear operator, which is our weak form, at ak. Okay, and since the right hand side is always the same, it cancels out for computing f prime. Well, we have some problems. Clearly, if we look here, let's see where are the problems. The first problem is we have to evaluate nu at the curl of ak plus s, but we don't know s, we just have to compute s. So this is something we cannot do. It is fulfilled here, yeah, because ak should be the solution, or is, better say, the solution of the previous time step. So in this sense, this is not a problem, but this here is a problem. So we do now the following steps in order to get rid of our problem, and that is we add and subtract this term. Yeah. So let's have a look what we are doing actually here in this sense. So this is the term we add and subtract, so which means, yeah, we don't change anything. But as you see, it is the evaluation at AK, the curl of AK plus S. We also have here AK plus S. And so we will get here the difference between the evaluation of our material parameter nu in this sense at the curl of AK plus S and the curl of AK. And then we can more or less develop this function in a Taylor series and get then rid of the necessity to evaluate it at AK plus S. Okay, so if we now do this, as I have told you, we will combine this and this with the minus sign, as you can see here. And what remains here for the plus sign is that this term cancels out. Yeah, it is just a term where we have AK, AK. Don't forget that the curl of AK plus S is the curl of AK plus the curl of S. So in addition, we get here this term. So in addition, we get here this term, and this term, what we had here, cancels out due to the fact that we add this strong term here, and we have the curl of AK plus S is the curl of AK plus the curl of S. Okay, so now we have we need a closer look on this term here, yeah, and this term we will evaluate in a Taylor series as shown here. Okay, so we have now it written down, and already the following: we have to evaluate our relativity at the curl of AK plus S and the relativity at the absolute value of the curl of AK. And since we develop the first term here into a Taylor series, so this term we evaluate in a Taylor series up to first order, and we subtract here the value at the curl of AK, what remains is mu prime, as you know from a Taylor series, scaled by the increment. And the increment is clearly the curl of AK plus S minus the curl of AK. But important is that we do not have to evaluate here this material parameter. It's now the derivative of the material parameter at S, which we don't know. We just have to evaluate it at the curl of AK, and AK is the solution of the previous iteration. So what we in addition now have is this increment, the absolute value of the curl of AK plus S minus the absolute value of the curl of AK. And this we can rewrite in the following form, as you can see, because what we consider here is the simple relation a squared minus b squared is equal to a plus b times a minus b. Okay, so this is a plus b. So this here is a plus b. This is a minus b. So in the nominator, we should have the absolute value of the curl of a squared. So a squared minus b squared. Okay, so we now have a look on this term, a closer look, and we'll try to approximate it in a senseful way. And that is already shown here. So we have the same denominator, but in the denominator we evaluate this square. So we have, since the curl of AK squared plus the curl of S squared minus what we have here, 2 times the curl of AK dot curl of S, minus clearly the term, the remaining term, which is the part here. Okay, now since we assume that the increment S is small in a L2 norm, for example, towards AK, we neglect it here. So I just take another color out. So we will neglect this part here. We will be also able to neglect any squares. Yeah. So this is to the approximation up to first order. Yeah. And then we should not forget that we have here these two terms. Yeah. When we subtract, it is 0. Which means these two, and these two terms added will cancel out, and we have a final expression for it, that it is the curl of S dot product curl of AK in the numerator, and then the denominator we have just the absolute value of the curl of AK, which is actually BK, be the magnetic flux density. Okay, so we also have now done this approximation of the increment here up to first order, always important. That is why the Newton method is then second order accurate. And what we get now for our Frechet derivative is nicely shown here. So our Frechet derivative can be approximated, and this is now just written here by this quite long term. So we have the derivative of our material parameter. Important, we just have to evaluate it at the curl of AK, so the solution, the previous solution. We have the curl of the increment for which we want to solve, dot product with the curl of AK, which we know, divided by the absolute value of the curl of AK. And then we have the curl of AK plus S, but we know the curl of AK plus S we can write as the curl of AK plus the curl of S, dot product with the curl of our test function, and this remaining additional term we already had on the other slide. Okay, so neglecting all terms of second order and using this relation, which I just have told you, we come up to the following approximation of our Frechet derivative in this sense. So we have to evaluate here the material parameter at the curl of AK, which is the previous solution, and we have all these long terms here and this second term. But now we have no problems in this sense. We have everything under control, because where we have to evaluate something, it's the evaluation of the previous solution within our iterative Newton scheme, and we can solve then for the increment S. Okay, so in this sense, just summarize it as shown on this slide here. And it is as follows. So we have our standard term plus this term, where we had a lot of work. And please consider here this relation that the vector b at iteration k divided by the absolute value of b at iteration k is the unit vector EBK, which we use heavily in this notation here. Okay, so you see our stiffness matrix within the magnetostatic computation is now ready to be approximated by the basis functions of the test function A prime and S. Yeah, and everything what is known we put to the right hand side, which is this term here with the current density, which is known, and this additional term coming up from the Newton scheme. But as you see, this we just have to evaluate it at iteration AK, and the new solution then is just that we add to AK the increment S. Now applying our approximation for S as well as for A prime according to the basis function, we obtain our finite element formulation as shown here. And this we even have divided into a standard stiffness matrix plus the tangential stiffness matrix. This overall system matrix is multiplied by the vector S, including all the unknowns, which are our increments we want to compute, and this is just the right hand side. So here, perhaps I just take this as green. So what we have here is as follows. So this part, what I have here, this part, this really gives us this term here, and this part gives us our standard stiffness matrix as which is this one, multiplied by the unknown increment s, which we want to solve. Okay, so that is a very nice formulation. In this sense, very appropriate, because you can also neglect this tangential stiffness matrix, and then you come up in the standard fixed point method. Yeah? So you can even switch then during the iteration between a Newton step and the fixed point step as shown here. What is still open, and we will also have to discuss a little bit, is the very important parameter eta, this line search parameter, which you should include for both for a Newton step as well as for a fixed point step. Okay, so let's have a graphical interpretation of our fixed point method. So the fixed point method is shown here. We have here our right hand side f, which we have to meet. You see here the nonlinear curve, and when you do a fixed point method, we always go along a slope and we come up to ak. So this is the new iterated solution, and then we again go along such a slope. So it can take a lot of individual steps until to come up to the solution. So this here is the point where the nonlinear curve meets the right hand side and will give us the solution here at the axis where we put the electric vector potential. Okay, this is the illustration of the Newton method, and as you know, for the Newton method we really always go in tangential direction. I try to show it to here, and so you see, if you are quite near, you need very few steps in order, and this is already the solution. In this case, after 3 times solving the equations, you get more or less the solution. Okay, now let's have some details on this parameter eta, and clearly it would be great if we can find a method to get the optimal, as it called, relaxation or line search parameter eta. For this we have to set up a functional as shown here and minimize it. What could be a functional? So a functional for this could be the following, that we project the increment on the residual. Yeah, the residual is when we evaluate the difference between our left hand side and right hand side. Yeah, so this is our left hand side and right hand side, and if this is 0, we are at equilibrium, we are at the solution clearly. So in this sense, this is the residual, and we take the dot product with the just computed incremental values we have obtained for the magnetic vector potential. Yeah, and we can, for example, now do a simple quadratic function for this g, which could be a0 plus a1 eta plus a2 eta squared. Yeah, and we know when this has a minimum is when the derivative with respect to eta is 0. You simply can compute eta out of the coefficients a1 and a2. And well, the evaluation g at eta equals 0 is already we have done in the previous iteration. This is what we obtain when we have solved, and then we have in addition to evaluate at eta equal 0.5, and we can simply compute the minimum. Okay, so this is a possibility. There are a lot of other possibilities, but it's a possibility which is quite robust. What we clearly also need are error criteria in this sense, because we solve a nonlinear equation, and a nonlinear equation means, well, what is the exact solution? You will get the exact solution, but we should stop our iteration when the error is quite small. But what is the error? The first idea is going to a so-called error criterion. So we just check the solution, the new solution, and check how far away the new solution is from the old solution in the L2 norm. Yeah. So you take each component of your solution vector, take the difference, square it, and sum it up, and then take the square root as shown here. And if this is smaller than some given epsilon, because it's an absolute norm, then you can stop. Or what makes perhaps more sense is to take a relative norm, which means that we scale the epsilon by the L2 norm of the current solution we have computed. Okay, so this means we just look for the measures between the new solution and the solution before, so ak plus 1 and ak. Another possibility would be to look at the residual, because if the left-hand side minus the right-hand side is 0, we are somehow at the solution. And that you can do in an absolute norm, or you can do as shown here in a relative norm. So I advise always to use relative norms, and what I also advise is to use and check within your implementation both norms. So also some value for the relative accuracy, what makes sense. So a good value is here 10 to the power of minus 3, which would mean you have accuracy which is about 0.1%. Okay, now let's have a look what can happen when you use just one of these error criteria. So in this sense, for example, you just check the error criterion, and we have a nonlinearity which is shown in this graph here, meaning that here you have a very strong slope, and then it is clear that in the error criterion the value will be quite small, but as you can see here, you are still far away concerning the residue. That can happen when we have this one. On the other hand, you can have a nonlinearity which looks like this. You measure in the residual criterion, and you have this kind of nonlinearity, as you can see here. Yeah? Well, then it could be the case that, as you can see here, the residual error is quite small, but you are still far away between your current solution, ak plus 1, and the correct true solution, a star. And that is why I always advise, please use and check both error criteria, and you are on the safe side. So let's look at a simple example. We have here an iron core, and around the iron core at one part we have a coil as shown in red here. It is a 2D example, so it's a cross section. Well, and we know clearly that the magnetic field will have closed field lines which will go along and mainly be concentrated within the iron core due to the high magnetic permeability. The direction is the question how the direction of the current is. You know, we have the right hand rule. Okay, so this is the solution for a linear computation. Well, you see that you have really no homogeneous magnetic field, which is, according to measurements, not really correct. And you see especially very high value at the corners. So these corners. And that is due to the fact you have a fixed constant magnetic permeability within the core, and that is not reality here at the corner. It will go to saturation, and then also the magnetic flux will also have field lines more outside as shown here, and that is as you do then a so-called nonlinear computation. You see here very nicely that we get here a more or less homogeneous magnetic field over the cross section, over this cross section here also for the others one. Clearly we have here quite low values, but that is also explained physically. The magnetic field lines want to go the shortest way, which is exactly this way here, but due to the fact that we take into account the nonlinearity, we get here in saturation. You see especially this finite element has the highest value. That's also in the other corners. And due to the nonlinearity, you get a physical correct distribution of the magnetic field, and you see how important